Welcome back. In this section, we're going to look at continuity, and to do that, we're also going to need to talk a little bit about one-sided limits. Informally, when we're talking about continuity for a function, we usually describe it with words like we can draw the curve in one line without having to take our pen off the page. That's normally how we describe it to people casually, but of course, as we know by now, in calculus, we need to have firm, definite definitions of what does it mean in order to tell whether a function is continuous or not. So definition for continuity at a point. We'll start with that, and then we'll talk more generally about continuity in an interval. So for a function to be continuous at that point C, you need three things to happen. Number one, there needs to be some sort of function happening there at C. You need to have something happening on either side of C. So in other words, the limit as x goes to C approaches, x approaches C for that function exists. So the y values need to be getting close to something as x gets close to C. And what the y values are getting close to is exactly what's happening at C. That's what the third little bullet point for our continuity definition is. So if any one of those parts are not met, then we've got a function that's discontinuous. And that's a lot of times what we'll be interested in thinking about first before we tackle a problem. Where are any discontinuities? We're going to see throughout this course that lots of theorems will start off with, let f be a function that's continuous on this interval. So it's always important for us to be able to tell where is our function continuous, because lots of theorems that we'll learn throughout the course will hinge on that. So first we have continuity at a point, and then we extend it further and say continuity on an open interval. If you're continuous on every point inside that open interval, then you are continuous on that open interval. So there we go. That's what continuity over an interval means. And of course, if you wanted to go one step further and say, what if something's continuous for all real numbers, then you could say it's everywhere continuous. So we've got this function, and it has a lot of discontinuities, and the question is why? Why do we have those discontinuities? So first thing that I would look at, I noticed that my first little discontinuity happens here at x is -1. And the reason I have that discontinuity is because f of -1 does not exist. There is no y value, so that's why if you were trying to draw this function, you would have to lift your pen off the page to continue to draw it, and that's because there's a hole in our graph when x is equal to -1. There's definitely the limit exists, there is a limit happening, so we have one of the conditions met, but we're missing the first one, which is there has to be something actually happening at -1. At 3, there is something happening, so we do have f of 3. F of 3 is 1, but if I look at the second condition, limit as x goes to 3, I would say, well, there isn't one because the graph is doing two different things on either side of 3. On the one side, it's approaching 2, and on the other side, it's approaching 1. So I would say the other discontinuity we've got at 3 is because the limit as x approaches 3 for our function does not exist. And I can also say the same thing is happening at 4. Also, the limit there does not exist. This one, the limit doesn't exist because the graph is approaching two different real numbers. Here, the limit doesn't exist because the graph is approaching infinity on the left side and on the right side. Either way, that's another reason why we have a discontinuity. So limit as x approaches 4 for our function does not exist. So that's 3 discontinuities so far. And then there's one more discontinuity, and that happens to be at x equals 6. There's definitely an f of 6. F of 6 is 3, so we do have a y value. We also have a limit. So as x is approaching 6, the y values on the right and on the left are approaching, looks like negative 2 point something or other. But unfortunately, what the y values are approaching and the actual y value are not the same. So the other one that we're lacking, the other discontinuity, the one that's at x equals 6, is because we do have that f of 6 is not the same thing as the limit as x approaches 6. So we had a limit, we had a value, but the two things were not equal to each other. So 4 discontinuities. For where are we continuous? Well, I would say we are continuous all the way up to negative 1. So here's some intervals. So everybody from far left to negative 1. Between negative 1 and 3, we're continuous. We're continuous in this little piece between 3 and 4. We're continuous between 4 and 6. And we're continuous when we're greater than 6. So we've got all those little intervals that we're continuous on and 4 discontinuities. And notice all the different kinds of reasons you can have discontinuities. You could have a discontinuity because of a hole, or maybe a skip or a jump, or a vertical asymptote, or again, another kind of a skip or a jump. So since there's different kinds of discontinuities, we might want to classify them as being removable or non-removable. Removable in the sense that if I redefine my function f of x at that point where the discontinuity is, can I fix it? Can I fix my problem? So just sort of circling back on my graph for a second here, there are definitely ones where you can fix the problem because we're changing one little point, and there are ones where you can't. And the thing to notice here, of course, is if you're redefining f of c, that is not, of course, going to change what happens near c. So in other words, your limit, that part of it, you won't be able to change. But you will be able to change what happens at x equals c. So for you to have a discontinuity that's removable, you would first need your limit to exist. If your limit didn't exist, then doing anything else to c is not going to change your limit existing or not existing. So if we look back at the ones in the previous slide, the ones where the limit doesn't exist, which would be at 3 and at 4, there's no value that I could give to this function at x equals 3 that would change what's going on the left side and the right side. There's no way that I can fix the break that I would have in this function. Same thing with what's going on at x equals 4. Even if I were to define any single value at x equals 4, that won't change the fact that the graph is diverging to positive and negative infinity on the left and the right side. On the other hand, the other two discontinuities I could fix. I could, for example, define f of negative 1 as the y value that would fill the hole, in which case I would have a nice continuous graph. Or I could redefine my y value so that f of 6 fills that hole. And again, I would be able to have now a continuous graph. And I could do that because for both of those, for at negative 1 and at positive 6, the limit did exist. So when we're asking ourselves to look at a function and determine where we have removable and where we have non-removable discontinuities, we first have to ask ourselves, where does the limit exist? Because those are the places where potentially we'd have removable discontinuities. So now taking a look at this one, if I were to say which points on our graph are we discontinuous, we're discontinuous at x equals negative 1. We're discontinuous at x equals positive 1. And we're also discontinuous at x equals 3. As far as is it removable, at negative 1, the answer is yes, and the reason is I could redefine my function so that what's happening at negative 1 matches up with the limit. The limit as x goes to negative 1 looks like is 1, so if I were to say f of negative 1 is 1, that would fill in the gap and that would make it a removable discontinuity. So I would say yes to removable at -1. At 1, on the other hand, the limit doesn't exist. On the left side, we're getting close to 2, and on the right side, we're getting close to 1. So no matter what I do to my y value at 1, that's not going to change the fact that the limit does not exist. So I won't be able to fix that. That's not removable. At 3, we have a little bit of a jump there. There's definitely a limit as x approaches 3. The y values are getting close to -1. So if I said, well, I'm going to change what f of 3 is and redefine it as f of 3 is -1, then that would mean I'd no longer have a skip in my graph. I would now have a continuous function at x equals 3. So I would say, yes, it's removable at x equals 3. Okay, so now let's look at each of these functions, and we want to figure out where each is continuous. And for all the discontinuities, where are they? Are they removable? Are they not removable? So for the first function, f of x, this is a polynomial. And this is something that we're going to make a bigger statement about a little bit later on. But right now, I can say for this that this is going to be continuous everywhere. And the reason for why it's everywhere continuous is because, remember, to be continuous, you would have to be defined at that point, you would need a limit to exist at that point, and you would need the y value to be the same thing as the limit. And this is because f of x is a polynomial. I know that f of c exists everywhere. And that's because, again, polynomials are defined for all real numbers. And I also know that the limit as x approaches c from our polynomial is going to be the same thing as f of c. And that's from an earlier result we had back in 1.3 where we said for polynomials we would evaluate their limits with direct substitution. And that was, in other words, saying that if we wanted to find our limit as x goes to whatever for f of x, we would just evaluate f of x at that point. So those connected together, the fact that we have y values everywhere and they are equal to our limit, so in other words, the limit exists everywhere and is the same as the y value, our polynomial is continuous everywhere. And again, that's something that's going to be true for any polynomial, continuous everywhere on its domain. So that's going to be something I'm going to make reference to going forward. We don't want to have to look at limits all the time unless we have to. And so for things where I know because of the kind of function it is, it's continuous in certain places, I'd like to be able to rely on that. And polynomials are one of those places. So that helps me out here with g of t. I can definitely say with g of t that this is also one where it's continuous in most places. If you're bigger than 0, you're a polynomial, you are continuous. If you are less than or equal to 0, or if you're less than 0, you're a polynomial, you're going to be continuous. At 0, though, that's where things are changing, and so that's a possibility that maybe the limit might not exist. There's definitely something happening at 0. If I wanted to know what is g of 0, I could say, well, that's using the second part of the definition. When t is 0, g is also 0. The question is, does the limit exist as t approaches 0? And if so, is it the same thing as our y value? And I can just take a quick look at a graph here to know that the answer is no to this. For values of t that are less than 0 or equal to 0, we're equal to g of t is equal to t. So in other words, looks like that straight line with a slope of 1, y-intercept 0. And if t is bigger than 0, the graph is t plus 1. So y-intercept of 1, and of course that's y-intercept that's a whole since it's t bigger than 0. There we go. And slope of 1 as well. So I can definitely see here that the limit as t approaches 0 of g of t does not exist. And it doesn't exist because the graph is doing different things on either side of 0. So this is discontinuous at 0. And this is also non-removable. And it's non-removable because the limit did not exist. If the limit existed, then we could redefine what's happening at 0, and that would make it nice and continuous, but too bad for us, that's not the case. So P of x, that's one that we're going to want to look at and sort of think about rewriting it first, maybe, because for P of x, the way that it's written, we've got an absolute value function in there. And I know for absolute values that really I could think of them as being piecewise defined as far as what's happening when we are inside is positive and what's happening when the inside is negative. And then how does that affect what P of x simplifies to look like? One thing that's definitely for sure true if I'm looking at this though, x cannot be equal to 0. So definitely we're going to have a discontinuity at x equals 0. And the reason for that is that right now, currently, f of 0 does not exist. It's not defined. So if a limit exists, then this would be a removable discontinuity. So that's a good question. So let's figure out if that limit exists. And to do that, I'm going to rewrite p of x, and I'm going to rewrite it as a piecewise defined function. So if we're talking about this, it's going to be really over two intervals. One interval where x is bigger than 0 and the other one where x is less than 0. X being equal to 0 is not being included because remember I said that x equals 0 is a discontinuity. So what do we have for p of x? Well, if x is positive, then the absolute value signs aren't really doing anything for us because positive number cubed is already positive. So p of x is really x cubed over x. But of course, that's really the same thing as just x squared. So in other words, our graph is graph of x squared when we're to the right of 0. And if I'm looking at to the left of 0, I'd say, well, if x were negative, x cubed would be negative, and then the absolute value sign would change that. So the absolute value would give me the opposite of x cubed over x. And then the same thing as before, I could simplify and say, well, really, x cubed over x is the same thing as x squared. So p of x is actually the function that's doing two different things. It's doing parabola opening up when we're to the right of 0, and it's doing parabola opening down when we're to the left of 0. For this one, for sure, we can see that the limit does exist. The limit as x approaches 0 of p of x is 0. So we could fix this. This is removable. The discontinuity is removable. If we were to let f of 0 be 0, if we redefine and said the y value at 0 is 0, then the limit would approach 0, the y value would be 0, that would fill in our little gap there, and we would have a nice continuous function. Okay, two more to look at. The first one, h of x. Again, you can see two places where this function is not defined. So these are two places where we're going to have discontinuities. We're going to have a discontinuity at x equals 0, and we're going to have a discontinuity at x equals -1. So the reason for both is f of 0 does not exist, and also f of -1 does not exist. And that's because currently, as it stands, you've got an x and an x plus 1 in the denominator. So at 0 and at -1, the denominators are 0, and we have it doesn't exist. You will notice, though, that I could simplify this function. The x's would cancel, which means that if I were looking at the limit as x goes to 0 of x over xx plus 1, that limit would exist. And that limit would be 1. So since x equals 0, the function doesn't exist, but the limit does, then that means this one is removable. If I said f of 0 had a y value of 1, then the limit would match up with the y value. We'd have a nice continuous function. Right now, what we have is a hole. We have no y value at 0, but on the left side and the right side, the graph is getting closer and closer to 1. So we have a hole, in other words, a removable discontinuity at 0. And at -1, we're going to see that for that one, the limit does not exist. Because if we look at the limit x goes to -1, even after we've canceled the x, we get something where the numerator is a constant and the denominator is going to 0. This limit does not exist. So the limit of x approaching -1 of 1 over x plus 1, that one does not exist. So that means that at x equals -1, that limit does not exist, which means this is not removable. Okay. Last one, and this one's a trig one. Conveniently enough, though, we have two functions in there, secant and tangent, that have a bunch of places where they're undefined. And conveniently enough, they're undefined in the same places, which is sort of nice for us. So for both of those, secant and tangent, they're not defined at pi over 2, positive or negative. They're not defined at pi over 2, both positive and negative, 3 pi over 2, all positive and negative, and so on. All of those odd pi over 2s. So plus or minus pi over 2, 3 pi over 2, 5 pi over 2, and so on. Those are all places where tangent is undefined and also where secant is undefined. So I already know that those are going to be all places where we are discontinuous. So the question is, what kind of discontinuous are all these ones? So here, the thing that I notice is that for s of theta, you could rephrase this as taking a cosine out, leaving a tangent squared plus 1 behind. And I noticed that that actually would fix a lot of my problems, because tangent squared plus 1 is the same thing as secant squared. And so the secant squareds would cancel, and I'd be left with s of theta would simplify to be the same thing as cosine. So that means that although we have s of theta not existing at any of those points, the limit as theta goes to pi over 2 for s of theta exists, and so does everybody else. So negative pi over 2, 3 pi over 2, 3 pi over 2, and so on. All of those limits exist. As theta goes to pi over 2 for s of theta, that's theta going to pi over 2 of cosine, which is just 0. Or negative pi over 2, which is also 0. Or 3 pi over 2, which is also 0. Or negative 3 pi over 2, which is also 0. So actually this function, even though the function doesn't exist at any of those points, the limit exists at all of those points, so that all of these points are removable discontinuities. So they're all removable, and conveniently enough, they're all removable with the same y value. In fact, the limit for theta approaching any of those values for the function s of theta, it approaches 0. So if you let s of pi over 2, negative pi over 2, and everybody else all be equal to 0, then you would have filled in all the holes, and you would now have your discontinuities removed.